I think this is going to be the last of our momentum videos. What we're going to talk about this time is the idea of impulse. We discussed it briefly in class. I thought we'd go over it just one more time because it's going to be our lead into forces. So impulse, for some reason, we use a J for. Don't know why. If you want to look it up, good by me. But I don't know what it is. I don't know why we use a J. Now, impulse, the way that we're going to look at this is by imagining two objects running into each other and sticking. Say it's mass moving with a velocity of v towards another mass who is at rest. After the collision, the two objects stick together, m plus m. And we can easily see that mv over 2m is going to give me a final velocity of v over 2. Now we see in this thing that for the system, momentum is conserved, which is great. We need that to happen. Conservation of momentum is an important thing. But if we look at each individual mass, call that 1 and 2, if we look at mass 1, its initial momentum is mv, its final momentum is m, because that's just the mass that we're talking about, times v over 2. In fact, if we look at the change in momentum, it's going to be negative mv over 2. We have lost some of that momentum. Well, let's see what happens to mass 2. Mass 2, the initial momentum is 0, and the final momentum is m times v over 2. In this case, our change in momentum is positive mv over 2. So we see in this collision that the first mass loses some momentum and the second mass picks that up. So as a system, the momentum is conserved. Now the people that did sort of the work on momentum before Newton, Huygens and Descartes, well, they did it before Newton, and Newton looked at this as he was coming up with his laws. And as we see here, something made this lose momentum while at the same time this gained momentum. But whatever that something was happened equal and opposite. This is where we get Newton's third law, the idea that forces occur in equal but opposite pairs working on two different objects. Sorry about that. Sometimes we malfunction. So, in this collision, the first mass experienced a force this way, which changed its momentum by this much. The second mass experienced the same force in an equal and opposite direction. We will talk about some of the tricky things with forces when we get into that unit. It's just interesting to see that this change in momentum thing leads into Newton's third law. So the next part, let's just talk in general. The change in momentum for any one given object in a collision as it's dealing with something is the mass of the object times the change in velocity of an object. So if we take this change in momentum and we divide it by time, so we're going to have change in momentum over time is equal to mass times the change in velocity. That's supposed to be a change in over time. Well, we know what change in velocity over time is. It's mass times acceleration. So this thing of change in momentum over time is going to describe how the motion of an object changes. Well, that's the force acting on the object. Force is equal to the change in momentum over time. This is the second law. Essentially, forces change the motion of an object. Since we're talking about momentum, it has that concept of mass thrown in there. The more mass we have, the more we're going to resist that change. But a force is the thing that is going to change that motion. This is where the whole idea of impulse comes in. If we just solve that for the change in momentum, force times the change in time is equal to the change in momentum of an object. This is the force-impulse relationship. So impulse is equal to force times the change in time is equal to the change in momentum for an object. And lo and behold, right out of conservation of momentum comes the second of Newton's three laws. So impulse is the change in momentum over time. That gives us another interesting relationship that we will be using on some problems in class and whatnot. But if we look at force on our y-axis and time on our x-axis, a graph of force versus time, let's say it's a collision, it's probably going to peak and then go down a little bit. The area here is equal to the impulse, or the area is equal to the change in momentum. I don't know why we talk about the two things differently, but impulse and change in momentum are the same thing. The area is in units of force times time. So if you get a graph describing the impact between two objects in a collision, essentially that graph is going to give you the change in momentum for each of those objects. For one of the objects it's going to be forward, for the other object it's going to be backwards. That's really it for that. We'll go over some examples in class, and you'll have some to do for homework, but that's all we got for momentum.